All right, I guess we'll begin. And I guess before I get into today's stuff, just want to check, see how everyone's doing. Got any questions? Got a thumbs up back there? That's great. All right, okay. That's great. Okay, you guys have a quiz today covering stuff from chapter 7. And then, and today I'm going to wrap up chapter 7, and then we're going to get into chapter 8. And just looking at our timeline, you know, our final exam is going to be 1 week from today, next Wednesday. And so, so really, as far as lecture material goes, I have today, and then I've got Monday. And I would probably prefer to spend Monday doing a bit of review and whatnot. So we'll see how far I get. I expect to be able to finish chapter 8 today. We might take a brief look at chapter 9 or not. I might have to. Maybe we won't get to chapter 9 during the summer. So so we'll see. We'll see how it goes. Okay. Well, let me kind of wrap up chapter 7 here. And in chapter 7, the big concept that I covered was the sampling distribution. Okay, so chapter 7, we had the sampling distribution of p hat. Okay, and the idea here is that you've got a random sample drawn from a population, and even though the population has a certain proportion, when you take random samples, the random samples will have proportions that are similar but not exactly the same, right? So the sampling distribution of P, we said the population has a certain proportion. Okay, and we call this the population proportion P. And the idea is each time you can take a different random sample. So these are samples. And each sample will have different p hats. And if we keep track of all of these, we're going to get a bunch of different p hats that can be approximated with the normal distribution. Okay. Okay, and that was the what the central limit theorem says. The central limit theorem says that the distribution of p hat is normal, and we can kind of use this and say that the mean is going to be p, and that the standard error, the standard deviation of this thing, is going to be p times 1 minus p divided by n. Okay. And you had some practice questions in your, so I posted a practice quiz, and you had questions like that, and you'll see very similar questions on today's quiz as well. Okay. All right, so this is what we had, and then we said, well, you know what? Most of the time when we are dealing with data, we don't actually know what the population looks like, okay? And instead, we've got a random sample, and based on this random sample that we currently have, we want to draw conclusions about the population, okay? So in most scenarios, we do not know the population proportion P. Okay, and it's something we want to make conclusions about this proportion P, even though we haven't observed it directly. Okay? We wish to make a statement about P, okay? And so the idea was, if I observe a P hat, because I know the central limit theorem says most of the time my P hats are close to P, if I kind of reverse that, and if I say if I observe a P hat, I can be confident that P is nearby, okay? So basically, the normal distribution says tells us that most of the time P is close, P hat is close to P, the mean. Okay, the normal distribution says most of our observations are close to the mean, close being something like within 2 standard deviations, okay? So the reverse is true. Reverse is also true. If I observe P hat, I can be confident that P is close by. That P is close by, okay? So that's so we covered last week. We said if we know what the population proportion is, we can make a normal distribution to say, you know, what values of P hat we're going to get. And now we're doing the reverse. We're going to say, if I've observed a P hat, I can be confident that the population proportion P is close by. And so, so using that, we created our 95% confidence interval. Okay, and we said we are 95% confident that P, the population proportion, is within 1.96 standard errors of P hat, okay? So our 95% confidence interval looks something like this. P hat plus or minus 1.96 times the standard error. Okay, and the standard error is estimated by using P hat instead of P. Okay, so in the normal distribution, the standard error looks a lot like this, except we don't have the P hats. But the issue here is that we don't know what P is, so we're going to estimate the standard error by using P hat instead, okay? And so if you look at, in the textbook, it talks about the standard error and it distinguishes the standard error from the standard error estimate, right? So we get SC EST. Okay, and so here, let me just do a quick example. So the example is, we get a random sample. We'll say 100 people. And of the 100 people, we'll say 30 of them I don't know. 30 of them have seen some movie. Okay. Okay. I've seen the movie, whatever. Blah, 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 blah. Okay. All right. So, whatever movie we're talking about, we're going to say 30 of them. And so the question is, what proportion in the population have seen the movie? Okay. So in your random sample, if 30 of them have seen this movie, what does this say about the general population? Okay, so here our p hat is 30 out of 100. We have 0.3. Okay. What can we say about the proportion in the population that have also seen it? Okay, so here I'm going to just kind of use this and make a 95% confidence interval. And this is going to go from p hat 0.3 plus or minus 1.96 times the square root of p hat, which is 0.3, times 1 minus p hat, which is 0.7, divided by n, which is 100. Okay, so I'm going to go ahead and I'm going to just run this on the calculator. Okay, so I'll do square root of 0.3 times 0.7. Okay, divided by 100. Okay, and I get 0.0458, and I will multiply that by 1.96. Okay, and I get 0.0898. Okay, so this becomes 0.3 plus or minus 0.0898. Okay, maybe I'll just do 0.09, okay? Anyway, so this is what I've got. This part over here, this is also known as our margin of error. Okay, so basically my 95% confidence interval is going to be 0.3 plus or minus 0.09, just to kind of keep it easy, right? And so this tells me this is 0.21 to 0.39, okay? So if my margin of error is around 9%, I guess according to this it's 0.0898, okay, but very close to 9%. Then my confidence interval goes from 0.21 to 0.39, okay? And I would say something like, okay, so what this means is that if I surveyed 100 random people and I find that 30 of them have seen this movie, then this tells me that in the population that I can be confident that somewhere between 21 and 39% of the population have seen the movie as well. Okay, and we don't know if it's 21 or if it's 39. We can just say that these are values for the population proportion P that are likely to kind of produce a sample where 30 out of 100 have seen it, right? So if in the population only 21% have seen it, you know, that might be the case, and it's possible that by random sampling, we happen to get a sample where 30 out of 100, a few more than the population have seen it. And the flip side is also quite possible. That in the population, if 39% have seen it, it can produce a random sample where only 30 out of 100 people have seen it. Okay, because of random sampling, sometimes you get too many and sometimes you get too few. So this is what we've got: 0.21 to 0.39, 95% confidence interval. And I would say something like, I am 95% confident that between 0.21 and 0.39 of the population have seen the movie. Okay. Is that all right? Now, is it possible that 40% of the population has seen the movie? Okay, it's possible, but that would be surprising to us. Okay, so let me, I'm going to flip the slide here. Okay, so my 95% confidence interval goes from 0.21 to 0.39. Okay. Is it possible that in the population 40% have seen the movie? Okay. And the answer is yes, it is possible. It's not impossible, okay? But we would be surprised, okay? Okay, and why would we be surprised? The reason why we would be surprised is that in our sample, only 30 out of 100 people have seen the movie, okay? But we would be surprised, okay? Our sample had 30 out of 100 seeing the movie. Okay? Which means that if in the population 40% have seen the movie, then that means something really unusual with my random sampling happened, okay? So it's possible that in the population 40% have seen the movie, but then it just means my random sample just happens to be this very kind of unique sample, okay? Our sample had 30 out of 100 seeing it, and so if the population was 40%, I'll say it has proportion 40%. Something kind of unusual. Okay, so something unusual happened during our random sampling. We're not saying it's impossible, but we're saying something unusual happened. Okay. Other questions could be something like, do we have evidence that the population proportion is different from 0.4? Okay. So this question sounds similar to the previous one, because the previous one says, is it possible that in the population 40% have seen the movie? And here I'm asking, do we have evidence that the population proportion is different from 40%? The answer to this one is that we do have evidence that it's not 40%. Okay, it's possible. It is possible that it could be 40%. This previous statement is true. It's possible that it could be 40%, but we have evidence that it's not. Okay, we have evidence that it is not 40%. Okay, yes. Okay, and I want you guys to be comfortable with kind of those notions. Okay, you can have evidence that something is not the case while that thing is still possible. Okay, it is possible that the population is 40%, that the proportion of the population is 40%. It is technically possible, but we have evidence against that possibility. Okay, so we have evidence that the proportion is not 40% because basically our interval only goes from 21 to 39%. .39. Okay, 40% is outside of the interval, which means it is not like a credible or plausible value. Okay, we want to say, it's not impossible, but it's not really a credible or plausible value. Okay, the proportion 0.4 is outside of the interval. So it is not a plausible or credible value. Okay? We don't want to say it's impossible, but it's just not something that we're going to believe. Okay? So we can say, so basically the idea is, we can have evidence against a certain possibility. Okay, even if even if the possibility is not impossible. Okay. Okay. So in statistics, we don't ever really completely eliminate possibilities. Okay. Things are only eliminated if the possibility is truly zero. And that's fairly rare. Okay. Okay. So here it says, do we have evidence that the population proportion is different from 0.4? Let me just do like another kind of slide with some explanation here. Is this all right? Okay, so our 95% confidence interval is 0.21 to 0.39, okay? Someone asks, do we have evidence that the proportion is 0.30? I should say that the population proportion. Do we have evidence that the population proportion is 30%? Okay. And here we have to be careful. The answer is actually no. Okay. 30% is a possibility, okay, and it's certainly a likely possibility, but we can't come to the conclusion that the population is exactly 30%, okay? We're saying any value between 21 and 39% are plausible or believable values, but we're not ready to say that the population is has any one exact proportion, okay? So we have to say no, okay? Our confidence intervals tells us that 0.30 is a plausible value for P. Okay. However, it does not tell us that the proportion P is exactly 0.30. Okay. The only way we could know what the exact proportion of the population is to measure the entire population. We would have to ask and survey every single member of the population to get the exact proportion, which is not going to be not going to be an easy task. Okay. So the confidence interval gives you a range of things that are believable or plausible, but it will never tell you exactly what the proportion is, okay? On the other hand, if we say, do we have evidence against that P is 0.30, the answer is no. 0.30 is inside our interval. So it is a plausible value. Okay. Do we have anything against the claim that P is 0.30? Is that okay? Okay, so this kind of wraps up chapter 7, section .7.4. Oh, I'm sorry. There's a couple other things. There's one more thing I got to cover from that section. Okay, and the last is confidence levels. Okay. Confidence levels. All right. Our 95% confidence interval went from something like 0.21 to 0.39. Okay. Now, this is kind of the range of values that we believe to be plausible values for P. Okay. Now, if someone says, you know what, I want you to be even more confident about kind of the range that P is inside, okay? So if we want to be more than 95% confident, okay? If we want to be more confident that our interval contains P, what we would have to do is we would have to make our interval even bigger, okay? So this basically says we are 95% confident that our interval contains P. Okay, so remember, P is this unknown value. It's somewhere on the number line, and we're 95% confident that it's in between here and here. Okay, we don't know exactly where. If I want to be even more confident that P is in between my hands, I've got to just spread my hands out wider, and then I can be more confident that P is inside. Okay, if we want to be more confident, that P is within the interval, just ran out of battery. If we want to be more confident that P is within the interval, we must make the interval wider. Okay, so the 95% confidence interval is P hat plus or minus 1.96 times the standard error. And a 99% confidence interval is P hat plus or minus 2.58 times their standard error. So I think my standard error last time was 0.0458. So this was, 0.3 plus or minus 1.96 times 0.0458. If I want a 99% confidence interval, I would go 0.3 plus or minus 2.58 times 0.0458. Okay, so I'll multiply that by 2.58, and I would get plus or minus 0.118, okay? Okay, and so here my confidence interval goes to 0.418 and starts at 0.192. Or is it 182? 182. Okay, so I said, I'm 95% confident that P is between 21 and 39%. If I want to be even more confident that my interval contains P, I can just make my interval wider. And if I go down to 18% to 42%, then now I'm 99% confident that P is somewhere between here and here. Is that all right? Now, what would I have to do if I wanted to be 100% confident? If I want to be 100% confident that I'm correct about my proportion P, right? So right now we want to say, I think our silly example is, I surveyed 100 people and 30 of them have seen the movie, okay? And based on this, I want to know, okay, what proportion in the general population have seen it, right? So I'm 95% confident that somewhere between 21 and 39% of all people out there have seen this movie. If I want to be more confident, I can just make my interval wider. I can say it's got to be at least between 18 and 42%, okay? So I'm making a wider interval to be even more confident. If I want to be 100% confident that I'm getting it right, that P is somewhere in my interval, what would I have to do? What's the only way I can be 100% confident? 0 to 1, exactly. Okay, the only way I can be 100% confident about the proportion is to say Well, the proportion's somewhere between 0% and 100%, okay? And then I would be right every single time, okay? Whatever thing you're thinking of, I can say at least somewhere between 0 and 100% of people have done this thing, okay? It's not a useful statement, okay? To say the proportions between 0 and 100%, that's not a useful thing to say. And that's the trade-off that we have. We can be more confident that we're getting the proportion right, but the trade-off is that my interval gets wider and wider and wider to the point of it being no longer useful, okay? If I'm coming back and I'm saying, you know, well, I'm confident that somewhere between 0 and 100% are going to have this, then, you know, that's not useful for us, right? You know, for example, when like UCLA admits a bunch of students, right? Well, not a bunch, but a lot apply, and then they admit, and then they're expecting a certain proportion of those admitted to enroll, okay? Now, they have to kind of forecast and figure out, you know, they need to figure out what proportion of those that they've admitted will actually enroll. They always admit more, and then they're hoping that only a certain percentage will actually enroll, and that will have enough space for them, for everybody who chooses to enroll, okay? And usually they get it right, okay? But if someone says, you know, what percentage of those that we admit will enroll? And I have no idea what the numbers are, okay? But let's say it's like 60% of those admitted choose to enroll. Someone can say, well, you know, last year it was around 60%. So this year, you know, we're pretty confident that it's going to be between, and they can make up a number, right? It's going to be between anywhere from 20% to 90%, okay? That's not very useful, okay? Because if that might be true, okay? I'm 99.99% confident that it's going to be somewhere between 20% and 90% of those that we admit will enroll, okay? And that might be correct, but then, you know, what are you going to do with that? You have to now suddenly say, well, if 90% enroll, then we need to build a whole bunch more dorms or something like that, right? And so for your numbers to be useful, you need a kind of a smaller window. You got to say, okay, somewhere between 55 and 65% are going to enroll, or 58 and 62%, okay? You want to try to create a narrow interval because narrow intervals are more useful to us. We can get better projections and things like that. You know, just like planning a budget, you know, how much money are you going to make next month? And you say, well, I'm 100% confident it's going to be between $0 and $1 million. You are correct, but again, it's not very useful to have a super wide interval. So the flip side is if we're willing to trade away some confidence, we can make a narrower interval, okay? And so we've got 95%, 99%, and we can go down to like 90%. A 90% confidence interval is the same p hat plus or minus 1.645 standard errors. And at 80%, we would have p hat plus or minus 1.28 standard errors, okay? And so these are kind of the trades that we can make. We can shrink our confidence interval and have a more narrow range, which is generally more useful, but we have to now accept that there's a higher kind of chance that we'll be wrong, that our confidence interval is wrong, okay? So in general, narrower intervals are more useful. Okay. Narrower intervals are more useful. The trade-off is that we are less confident that P is inside the interval. Okay. I'll go ahead and I'll provide this table of values for you. So I'll provide these values on the final. Okay. Okay, but does that make sense that we can have a narrower interval, but we'll have less confidence about it? And if we want to be more confident, we have to increase the width of our interval. And that's what we often have. Okay, I am going to make the decision to skip section 7.5. Okay, so 7.5, you can read it on your own time in the textbook, but I'm going to skip, and I will not test on it. Okay, so we will skip 7.5. All right, and I'll cover chapter 8, and I will start to, I guess, post additional practice problems for you guys to start preparing and studying for the final exam. Okay, after today's class. Okay, so chapter 8 is on hypothesis testing. Okay, and we're going to just kind of stick with proportions, hypothesis testing for proportions. And hypothesis testing is another kind of inference where we have a sample of data, and based on the sample of data, we want to make conclusions about the population. Okay, so it's another form of inference. Okay, we start with a sample. And try to make conclusions about the population. Okay, so it's very similar to making a confidence interval, except we're taking a different approach. So the confidence interval, you know, we said here's what our sample looks like, what could the population look like? When we do a hypothesis test, we kind of start off with a claim. Okay, we start off with something which we call the kind of our hypotheses, and there's all this terminology. We've got the null hypothesis and the alternative hypothesis, but basically we start off with some claims, and then we say, well, if this claim were true, is it possible, you know, could we observe the data that we have? Okay, so in hypothesis tests, you know, we begin with a claim or and a pair of hypotheses. Okay, and we have something called the null hypothesis. Which is written as H0 or HO, okay? 0 like null, okay? And the null hypothesis is going to be something along the lines of the population proportion is equal to some number. The population proportion is equal to blank, okay? Or symbolically, we would write P is equal, we might call this P0, P0, okay? So we just say, so the null hypothesis says that the population proportion P is equal to some number, and right now, for now, we'll just call that number P0, okay? And then the alternative hypothesis, which we call HA, is going to be just kind of the opposite of that. The population proportion right? The population proportion is not equal to or is greater than or something like that. Is not equal to P0, which we would write P is not equal to P0. Or it could also be that the alternative is that P is greater than P0, E is not equal, or is greater than, or is less than. Okay, and this depends on kind of the question that's being asked. Okay. Right. So, you know, in advertising, people make all sorts of claims, and they always use kind of weasel words so that they can't get sued for false advertising and stuff like that, right? So it's like, you know, a 15-minute call could save you 15% or more, but they have to use the word could because maybe it won't. so you know, I could say, you know, a 15-minute call could save you, you know, 80% or more, and I won't get in trouble because I use the word could, and I say, well, it just didn't happen for you. But you know, let's say some company just comes along and they say, you know, over 90% of our customers are satisfied with whatever we were saying, right? So they make a statement, they say over 90% are truly satisfied. And let's say you are the FCC or something, some kind of agency, and you're getting complaints and they're saying, I don't think this is true. I don't think it's actually 90% of the customers are satisfied. So you need to test this, okay? So you know, some company says over 90% of customers are satisfied. Which I don't know if that's even something we should, but anyway, okay. We want to test kind of against this claim, or okay. And so basically, we are going to set our null hypothesis is that P is equal to 90%, okay? And so this is going to mean, so P is proportion of satisfied customers Okay? And here's the alternative. So we want to see if, is the company lying? Is the company lying when they say over 90% of our customers are satisfied? Okay, so we want to know, is the company lying when they make this, when they advertise this thing? Okay, so to test if the company is lying, for the alternative hypothesis, what should we use? P is greater than, P is less than, P is not equal to 0.9. We are going to use P is less than 0.9. Okay? Because if we do our thing and we survey customers and it turns out that 97% of them are satisfied, then we would not say that the company is lying, okay? Maybe the proportion is not equal to 0.9, but if it's over 0.9, we're not going to be upset at what the company is saying, okay? We would only actually be upset that the company is claiming that 90% of their customers are satisfied if the reality is that less than 90% are satisfied. If only 75% of customers are satisfied, then we would say, stop telling everybody that 90% of your customers are satisfied, okay? We would say, you can't do that, right? So the null hypothesis is going to be that the company's claim is correct, and the alternative is that they are wrong and that they are lying about their satisfaction rate. All right, is that okay? In other cases, you might just want to test for something that's different, okay? So it could just be like, in a previous study, we'll say, 55% of a certain species faced habitat destruction or something like that. I don't know. I've been watching all of these nature documentaries on Netflix. So this is what I've been thinking about. Okay. So we'll say, 55% of, kind of members of a certain species are facing habitat destruction. And we want to know, maybe we'll do a study today to see if it's changed, okay? Okay, and, a new study is done to see if the proportion has changed. Okay, so our null hypothesis and our alternative hypothesis. What would our null hypothesis be in this case? So the null always has an equal sign. Okay, we're going to say P is equal to 0.55. And then the alternative is going to be that P is different, that it has changed, okay? Has changed. Doesn't imply that it has gone up or it has gone down, okay? We would be interested in either case. Maybe conservation efforts have been successful and fewer are facing habitat destruction, or maybe things have gotten worse and more are facing habitat destruction. Either result would be interesting to us, okay? So the P is the proportion that faces habitat destruction today. Okay, something like that, right? So in either case, a change that, any change greater or less, okay, is of interest to us. Here, up here, we are only concerned if the proportion is actually less than 90%. Okay. All right. So that's how we start off. We start off by kind of stating these claims, and basically, the idea is if the null hypothesis were true, then certain types of data sets are more likely than others. Okay. So if the proportion is actually 0.9, if this null hypothesis were true, then when we take a random sample, values that are close to 0.9 are more likely, and values where p hat ends up different from 0.9, or significantly different from 0.9, are less likely. Okay, and so that's what we need to check here. Okay, and so so to carry this out, we will do conduct. I'm going to just kind of list off the steps for conducting a hypothesis test. Okay, and so for the first step is to kind of write your hypotheses. Okay, and just kind of keep in mind the null hypothesis will always have an equal sign. Okay, so read the question and figure out how to write your hypotheses. And the null hypothesis always has to have an equal sign. Okay. Part 2 will just kind of be some preparatory steps, okay? Preparation, and this includes a few things like kind of organize your data, and maybe choose a significance level, which I will talk about in a moment. And also check conditions to make sure it is okay to use the central limit theorem. Okay, so there's some steps of preparation here. Okay, and 3 is going to be do computations, okay? So the computations will be things like find the standard error, and then find the test statistic, and then find the p-value. All right, and I will define all of these things and talk about them in a moment. And then the last part is interpret and make your conclusion. So that involves making a conclusion about the hypotheses. Okay, let's try something out here then. Okay. Okay, so we'll do an example. And so all right, so this is just following an example from chapter 8. Okay, so this is a chapter 8 example in, I guess, section 8.2. Okay, and so we'll say, so I guess in Florida, it doesn't matter, 47% of registered voters actually voted. And then, okay, so then a researcher wanted to know basically people studying political science, do they vote at a different rate than the general population? Okay. And then so the data, so the researcher interviewed somehow 54 random people, poli-sci people. Okay. I'm not quite sure how this was achieved, but we're going to just assume that it was. Okay. So, and then 40 of them voted. Okay, so the question is, do people studying political science vote at a different rate from the general population? That's our question. And this is the data that we collected. 54 people were selected randomly from kind of this political science population, and 40 of them voted. Okay, let's set up our hypotheses. Okay, so first of all, what does our P represent here? P is the proportion of what? What's our population? It's a proportion of what population? Well, our question says, do people studying political science vote at a different rate, right? So this is going to be the proportion of basically poli-sci people who did what? Who voted, okay? So P is the proportion of poli-sci people who voted, okay? What is my null hypothesis? Is that this proportion is what? Is 47%. It's the same as the general population. That's the null hypothesis. The null hypothesis is that the proportion of poli-sci people who vote is the same as the general population. Okay, so basically poli-sci people vote at the same rate as the general population. I guess, general Florida population. Okay. And then the alternative would be what? Okay, so here it says vote at a different rate. Okay, so we would be interested if people in political science are more active in the, like, as far as voting goes, or maybe they're less active. Maybe after studying political science, they're disillusioned in the voting system or whatever and don't even bother. I don't know, okay? I think in our case, either would be of interest to us. Perhaps somebody else would just say, oh no, I think people who study poli-sci are more interested in politics and will then participate more than the general population. Maybe that's also true, okay? And if that's the case, then they would say, you know, do people studying political science vote at a higher rate than the general population? And we would have a greater than sign or something like that, okay? All right, is that okay with how I set up these hypotheses? Okay, the next part is then we do kind of our preparation. So, so one is we are going to choose a significance level. And I will get into this in a moment. But kind of the default, if you're not quite sure what to do, the default is what we call alpha. We'll say alpha is 0.05. Okay, and this is kind of where the threshold, if something happens less than 5% of the time, we say it is unusual, and if it happens more than 5% of the time, we will say it is not unusual. That's just kind of the rule of thumb, but depending on the circumstance, you might want to be more generous or more conservative with this rate of alpha, okay? So basically it's along the lines of if something happens less than 5% of the time, we say it's unusual. I'll say less than alpha. Okay, and so someone else might say, you know what, I want to shrink alpha down to 1%. So that if it happens, you know, 2% of the time, I'm not going to say it's unusual. I'm going to say, well, it happens 2% of the time. It's not that weird. Okay, but if it happens less than 1% of the time, I'm going to say that's unusual. All right, and that's the researcher's prerogative, okay? Whoever's doing the study can decide what they want to call unusual or not unusual, okay? So if it happens less than 5% of the time, a lot of people say, okay, that's unusual. But someone else might say, you know, if it happens 4% of the time, it's not that weird, okay? I'm not ready to say it's unusual. All right, when we do our math, we are going to simplify things by using the normal distribution. And we can do that because of the central limit theorem, which we covered last week, I guess. And the central limit theorem says that the sampling distribution of p hat looks like the normal distribution, but there's a few conditions, and I don't know if you guys remember what those conditions were. So the conditions are, we have to check conditions to use the central limit theorem, okay, which says that p hat follows the normal distribution. So first we got to just make sure that our data was obtained randomly and independent. Random and independent. Okay, and I'm going to just go ahead and give this a check mark. Okay, because it says, you know, we observed 54 people at random. I'm going to have to assume that they were selected independently, okay? 2, the large sample condition. What is the large sample condition? How do we know if our sample is large enough? We need 10 yeses and 10 nos, okay? How many yeses and how many nos do we have? Okay, well, I've got 40 yeses. 40 of them say they voted, which means how many do I have? How many no's do I have? 14, right? I have a total of 54 people, so which means we've got 54 minus 40, 14 no's. Okay, both are greater than 10. So we're good. Okay. And the population was not specified, but it says, I guess, all political scientists. So as long as the population, there's more than 540 poli-sci people out in the world, we're okay, okay? So the population isn't, we don't have numbers, but big population. Are there more than 540? Poli-sci people out there. We'll say yes, okay? And so we'll say that condition is also met. So it seems like it's okay for us to use the central limit theorem. Okay. And now we'll do our calculations. Okay. Okay. And the guiding question, the question that guides us is, if the null hypothesis were true, what is the probability of getting the data we have? Okay, that's the question that's going to guide us. If the null hypothesis were true, what is the probability of getting the data we have? Okay, so we said 47% of the general population voted, and our null hypothesis says that poli-sci people vote at the same rate. So the null hypothesis says that 47% of people studying political science vote. And what we observed was that 40 out of 54, okay? So 40 out of 54 is actually, much higher than 47%. And so, so the question, kind of, for the sake of argument, is just say, well, let's just say that the null hypothesis were true. What is the probability that we would get this proportion, okay? So the null hypothesis, again, was that P is equal to 0.47, all right? And we observed 40 out of 54, which means that, what is that, 40 divided by 54 is 0.7407. And this is my p hat, okay? So the null hypothesis says that 47%, when we take a random sample, we should get something around 47%. I got 74%, which seems much bigger than 47. So the question is, is it possible that from random sampling alone, I get 74%? Like, if the population truly is 47%, so if only 47% of poli-sci people do actually vote, is it possible that by random sampling, I got 54 people, and out of that 54, 74% of them voted? Could that happen just by random sampling? And we're going to say, well, theoretically, it's not impossible, okay? It's not impossible for something like that to happen. But something in our gut says, this is very unlikely to happen, right? So if I just paused here, right? And if we come to the conclusion that 74% is unlikely, what does this tell us about our hypotheses that we made? So if I go back a slide, I don't know how to actually do this. All right, so the question is, do people studying poli-sci vote at a different rate? Okay, and what do you think the answer is? Okay, just looking at our data. Is yes, right? We're going to say that 74%, that's probably not going to happen just from random sampling. It could, but 74 does seem pretty different from 47. So we're going to come to the conclusion that poli-sci people vote at a different rate. But we're going to back this up, okay, mathematically, okay? So we're going to just say, if the null hypothesis were true, okay, if it really were true, could we get this number, 74%, by random chance? And if we could, what is the probability of that happening, okay? So if the null hypothesis were true, could we get p hat equal to 0.74 because of random sampling? Okay, and the answer is always going to be yes, we could, okay? If yes, then what is the probability? What is the probability that p hat equals 0.74? Just not equal, but p hat is 0.74 or something more extreme. Okay, well, we know how to answer this question. This is a sampling distribution question, okay? This is what we have, okay? We have p hat comes from a normal distribution. What is the mean of p hat? If the null hypothesis were true, the mean of p hat would be what? 0.47, exactly. Would be 0.47, and then the standard error would be the square root of p times 1 minus p. I'm going to just plug in p0 here. Sorry, I'm going to back up here. Okay. So I'll just put in all the symbols first. So if the null hypothesis were true, this is what we would have. Which in our case would be 0.47, and 0.47 times 1 minus 0.47 divided by 54, and we would get a normal distribution, 0.47. My standard error turns out to be 0.0679. So here I am. I'm at 0.47 goes in the middle, and I'm all the way out here at 0.74. And I want to know what's the probability of getting 0.74 or something more extreme. And technically, I also want the reverse side, and I'll get into that in a little moment here. But let's go ahead and we'll do this. We want to know what's the probability that p hat is greater than 0.74, which turns into what's the probability that z is greater than, and for the z I'm going to do 0.74 minus 0.47 divided by 0.0679. And I get something along the lines of, so 0.74 minus 0.47, divide that by 0.0679. What is that? 3.97, 3.98. Okay. So the book says it's 3.99, something along those lines. Okay, we get a very big number. And what happens if I look up 3.99? It's not even on the table. Okay, 3.99 is such an extreme number, it is literally off the chart here, okay? It really is, right? It's off the charts. So so that's what it is, okay? We said values where z is greater than 2 are unusual. Values where z is greater than 3 is highly unusual. And here we're getting a value of z that's basically 4, okay, which is extremely unusual, okay. So basically, if it were 3.49, the amount in my tail is going to be like 0.0002, okay, or less. So I'm going to just write this is less than 0.0002, okay. It's a really extreme value. Actually, I think they have a few extreme values. Okay, actually, okay. So at -4, it's 0.00003. Okay, so a really small number, right? Which says, okay. So what that's saying is that, okay, if 47% of poli-sci people vote, is it possible for someone to randomly sample 54 people and find that 74% of them voted? Technically, it's possible. It's not impossible. It could happen. But how often does that happen? It happens with a probability of 0.00003. Okay? It could happen, but it's extremely, extremely, extremely unlikely to have happened by random chance, okay? So, this is the data that I actually have, okay? We sampled 54 people at random and we got 74% of them voting, okay? And so we have a choice. We could say, well, maybe I was that really, really, really lucky 0.00003, whatever, you know, I was the lucky, 1 in 10,000. That was me. That's my random sample. Or I could just say, you know what? I probably wasn't that lucky, and rather this assumption I made about poli-sci people is wrong. Okay, that it's not 47%, but that in poli-sci people, it's bigger than 0.47. Okay, I don't know exactly what it is, but whatever it is, it's bigger, and that's why I got 74% voting. Okay, so let me kind of write that down, all right? So the previous slide, we've got something like this. We'll put 0.47 here. I'm going to put 0.74 out here. And technically, we're going to also have the negative side, and we're going to say, so what we say is that so I'm going to just say my p-value is less than 0.0004, okay? Because this is p-value. We've got two tails. Don't worry about all of these details at this exact moment. I'll cover it in a couple minutes here. Okay, so my p-value is here, and this says, basically, is it possible to get 0.74 to get a random sample where p hat is equal to 0.74 if the population has proportion p equal to 0.47? And the answer is yes, it is possible. But it is extremely unlikely. Okay, it's extremely unlikely. It happens less than 0.0004 of the time. Okay, so because it happens so infrequently, and the fact that this is what I observed, okay, so our data has p hat equal to 0.74. So therefore, our data kind of provides evidence that the population proportion is not 0.7. Okay, because there's really only two possibilities at this point. Either the population proportion is 0.47 and my data is this really unusual, rare observance, or the population proportion is not 0.47 and my data is not that unusual of a happening, okay? Does that line of reasoning make sense? Okay, that because it is unlikely for our data to happen if the null hypothesis were true, the fact that our data happened leads me to believe that the null hypothesis is not true. Okay, so kind of our conclusion. Okay, our probability calculations show us that our data is unlikely to occur if the null hypothesis were true. Okay. So thus, the fact that we have our data kind of makes the case that our null hypothesis is wrong. Is that okay? All right. I'm going to go through section 8.4 where we're going to do a hypothesis test for 2 samples, and then we'll wrap up there, and then on Monday of next week. So after today, I'll post I guess some practice problems, stuff to help you start studying and preparing for the final exam. And so please work on those, and then on Monday we'll kind of review all of those exercises and kind of cover, more of this stuff, and we'll go from there. Okay, so I'm going to get into section 8.4, and this will be a hypothesis test for samples of 2 proportions. I'll say for 2 samples. And so, so this is an old survey, okay? But, and so this is example 14 from the text. Well, maybe it's a different number. Okay, but I guess, so remember earlier we had these two-way tables. And okay, so earlier we had kind of these two-way tables, and we said what are these things independent, or are they related? And earlier we said if they're different in any way, we're going to say that they are not independent. And now we can kind of do this thing as test it out. And so here our data just says, in 2002 they surveyed, do you support stem cell research? And these were the proportions. And in 2009 the proportions changed. Okay, and our null hypothesis here. Well, the question is, did the proportion of supporters change? From 2002 to 2009. Okay. And so the answer here is, well, we'll look at it, but the null hypothesis is basically that it did not change. The null hypothesis always has an equal sign, and the null hypothesis is basically P1 is proportion in 2002, and P2 will be the proportion in 2009. And the null hypothesis is that those proportions are the same. And here, because it just says, did it change, we're going to say that P1 is not equal to P2. Okay. The next part, we should check our conditions. Number 1 is set up our hypotheses. 2 is kind of the preparation. And again, we'll just use alpha equal to 0.05. And we will also do kind of check the conditions. And in the interest of time, I'm going to just tell you that the conditions are met. Okay? All right, so then the next part is when we do our calculations. Okay, and we are going to observe, the observed data will show, we'll have the difference p hat 1 minus p hat 2. This is the difference between the proportion in 2002 and the proportion in 2009, okay? If the null hypothesis were true, p hat 1 minus p hat 2 is expected to be close to 0, okay? Because the null hypothesis says that the proportion in 2002 and the proportion in 2009 are the same. And of course, because of random sampling, when you take a random sample and you get p hat 1, and you take a random sample and you get p hat 2, because of random sampling, those proportions might not be exactly the same. But if the null hypothesis were true, we would expect them to be close to 0. Maybe not exactly the same, but we would expect those two proportions to be close to 0. Okay? And so what we would have is we would get kind of this quantity, p hat 1 minus p hat 2. The quantity comes from the normal distribution where the mean is 0 and the standard error is going to be p hat times 1 minus p hat over n1 plus n2. Okay. No, I'm sorry. I'm doing this wrong. My bad. Times 1 over n1 plus 1 over n2. Okay. So our standard error, this is the standard error for 2 samples. And this p hat is the overall p hat. Okay, and so that's y1 plus y2, or is it x1 plus x2, whatever the total the number of successes, okay? Number of yeses, total number of successes divided by total number of observations, okay? So usually x1 plus x2 over n1 plus n2. Okay, so I think our data was something like this: 2002, 2009, 645, 855, and 870, and 630. Okay, so our p hat overall is going to be 645 plus 870 divided by kind of the total number of observations, which is 1500 and 1500. And I don't know what that is. 645 plus 870. 1515 over 3000.505. Okay. P hat 1, this is the proportion in 2002, 645 over 1500, and we get 0.58. I'm sorry, 0.43. Right, copying the wrong number down. And P hat 2, in proportion in 2009, 870 over 1500, and we got 0.58. Okay. So, we're expecting the two values to be kind of close to each other. We're getting 43% versus 58%, kind of a change of around 15 percentage points. And we want to know, is that a significant change, or is that kind of close enough? Could that be explained by random chance? So if the null hypothesis were true, we would expect this difference to be centered near 0. And so what we observe, are these numbers okay? I'm going to flip to the next slide. Okay. So again, we got P hat for in 2002, this was 0.43, and in 2009, P hat 2 was 0.58. Okay, and the P hat overall was 0.505. Okay, so we observed our observed difference is 0.43 minus 0.58. We get negative 0.15, and we have P hat 1 minus P hat 2. This comes from a normal distribution centered at 0, and the standard error is the overall P hat times 1 minus P hat overall times 1 over n1 plus 1 over n2. So this, we're going to do 0.505 times 1 minus 0.505 times 1 over 1500 plus 1 over 1500. And so this becomes a really small number, 0.018257. Okay, so if the null hypothesis were true, we would expect P hat 1 minus P hat 2 to be equal to 0, and here we are out at negative 0.15. Okay, and so we want to know kind of what is this area out here. And again, I think we're going to get this really extreme value. Okay, so we get negative 0.15. We're expecting this difference to be 0, and we're going to divide by the standard error of 0.018257. And when we do that, we get negative 8.22. Okay, so this is very, very, very extreme. Okay, z's greater than 2 are unusual, z's greater than 3 are highly unusual, and here we have a z more than 8 standard deviations away. Okay, so that's just ridiculous. That's a crazy amount. So anyway, this z is very extreme, which means that it's almost impossible for our data to have happened just by random chance. Okay. Occurred by random chance. while the null hypothesis is true. Okay, so the fact that our data did happen tells me that my null hypothesis should be rejected, okay? That we have this data tells us to reject the null hypothesis, okay? The null hypothesis that there was no change between 2002 and 2009. Okay, we will end there for today. I will post some practice problems, and I hope you guys can work on them by Monday of next week, and we'll go over them, and we'll spend some time to review in preparation for the final exam. All right, have a good weekend. We'll see you on Monday.